So I want to start with a question. How many in here through regulatory compliance have to do some form of alternative analysis to their current capital planning? All right. In the pipeline, how many people see that as a requirement that may be coming in the future? Okay, so several. I don't necessarily want to focus on non-wires alternative. I feel like it's a negative topic, and we really need to think of this as it's a requirement regionally and it's good in concept. You know, if you say, I have a capital investment, it's going to cost 10, 20, $30 million. What other options did you consider, and how did you justify those options? And I really feel like regulators are getting together state to state at a coffee shop and deciding that, you know, what we need to do is we all need Tesla batteries on our systems, and we need to consider solar and EV and what the impacts of those will be. And it's good principle, but it definitely complicates the planning engineer's life. So, you know, as a consultant, we go from utility to utility. So I want to cover a little bit about the things that we're learning, go through a case study and some of the things that we've learned about non-wireless alternative analysis and how we can apply that to just the traditional planning process. Next steps, and then we can take a few questions. So I'm excited, energized by the list of presentations we have. They're all focused on either how do we develop a better model, how do we do it more efficiently, how do we do forecasting, how do we consider doing a time series-based analysis, dealing with microgrids, using Solver for model builds and analysis. And I think these are great avenues towards not just non-wires alternative analysis, but doing a time series-based analysis. So we have a traditional planning process that's pretty common across the industry. So from any utility we go to, it's pretty typical. You do a peak analysis for capital planning. It's a conservative approach. You might do historical trending or some slightly advanced version of historical trending is pretty common for load forecasting. But historical trending only goes so far. And when we look through this advanced planning circle, we can take the historical load, but what it doesn't tell us is state change in policy. So if we say that EVs are going to be incentivized, how does that impact the grid? If we're going to say that, you know, we're going to have more DER through subsidizing the cost, or maybe just the cost in general comes down on batteries and solar and wind. So instead of a historical trend in which we then just apply a future growth, and if there's anything we know about load forecasting is there's uncertainty. So, you know, with certainty, I can tell you that whatever we project will be wrong. So what I think we need to do is, as we go through this cycle of planning, that we develop a probabilistic forecast in which we consider a sensitivity analysis of the model. So instead of running one peak analysis, you know, step in that next direction and say, okay, we'll look at seasonal, we'll look at off peak. Now we'll start considering time series analysis. Larry's talked extensively the last few years about, you know, we need to run 576, maybe it's a 24-hour profile, maybe it's 8760. You know, we need, depending on the analysis you're running, well, there's different use cases for each of those types of analysis. But it also varies, right? So if we have different penetration of EV and DER to consider, then not only do we have 576 weekday profiles for 12 hours, or no, 24 hours for 12 months for all of those different load types. Now we have it for different penetration levels of EV and DER. So coming around on the back end of this is now we've output all the data. What do we do with it? So we need to create new processes and algorithms that are capable of ingesting this big data and making sense of it, so we can continue to follow the traditional planning process, but we don't have to take 6 months to get the data ready. So I want to go through an example, and this is a recent non-wireless alternative case study that we worked with utility on. The particular problem in this region is that there's a subtransmission line that comes into a peninsula, It serves 3 substations, transformers, and then they have 5 circuits coming out of that those 3 transformers. Um, there's not a lot of contingency options. There's, in terms of switching, I mean, if you look out, one feeder goes out towards the end of the peninsula, and I mean, there's nothing to tie to. So it was a particular challenge in that not only was the system isolated from the rest of the system, it was not a tremendous amount of customers that are served by this area. It's mostly residential. It has historical, you know, we talk about forecasting and historical trending. They were seeing 8% growth a year for multiple years. So they were projecting forward 8% growth for multiple years. So if you do that over 10 years, you effectively doubled your load. So what we did for them is using Solver, we developed a load shape for each feeder for weekend, weekday, minimum and maximum loading. And then through the solver, we automated the analysis and then had some algorithms on the back end to take the data and consolidated based on planning criteria into clusters. So the reds and orange and yellows, that's all different sections that fell outside of the planning thresholds for this utility. What advantage that gave us is that we could go into this viewer, click on any section, see load shapes on every section, voltage profiles, and use that to help us in the development of what non-wireless alternative solutions we could consider in this area. In this case, we had transformer loading over 100%, conductor loading over 100%, voltage less than 117, and ultimately a big driver for cost was they wanted to have N-1 contingency for this area. So the traditional wired solution, which was developed prior to our involvement, was that they needed to spend over $100 million to build a transmission line through an environmentally sensitive area and come in on the backside to have a second path for power flow. And when that got pushed up, the feedback was, well, that's great, but you're routing this through an area that's environmentally sensitive, and it's a really expensive solution. Is there anything else that we should consider before we go through with construction on that? So talked a little bit about any section grabbing data, but as an example, what you can get out of the time series domain that you can't get out of a one peak evaluation is frequency and duration, which I think there's a lot to learn about in the capital planning process. If we just look at one run, we really don't know how often a violation is occurring. So excluding non-wireless alternatives, just in typical planning, the advantage we gain here is what we can say prioritization. So if you need to defer capital, you know, based on frequency and duration, the particular projects that are more or least likely to occur and higher risk possibly. But when we're looking at non-wireless alternative solutions, you know, a battery or solar, you can start to say, well, how often is something occurring? What's the duration? Is this something that a battery could resolve, or is the duration so long that I could never store enough energy cost effectively to offset peak? So once we went through this is a long item 1, by the way. Once we went through the problem statement, when you look through all the different solutions that are available, and we really trimmed down a list of what was reasonable for the region. You know, so we could have considered solar, but based on where it was at, hurricane risk and lack of available land, you know, we did throw out floating solar, but due to cost, it didn't really have any traction. You know, wind, battery, natural gas turbines, and we came up with a few different solutions. Now, look through the rest of these slides, but we got programs, demand response, CVR, energy efficiency. These are existing programs that we had to try to capture what estimated reduction we could get for the area based on the customer type. And then there's the things that were interesting, but ultimately not selected. You know, conversion to gas heat was something we'd considered in that. They had a winter peak that only occurred for a few hours out of the year, and it was nearly 20 megawatts higher than the summer peak. So could you incentivize customers to go to gas, which goes kind of against some of the principles of the utility, but it could save a lot in capital costs, and so you can defer some costs. So we end up with 4 scenarios: a base case, which was just the transmission upgrades, no outage, and then from a financial comparison, we looked at the transmission case with a 7-day outage, considering the economic impact to the customers in the area. Then you have a natural gas solution, which is distributing generation across the distribution circuit, and a mix of solution that also fed in what demand response, energy efficiency, and some battery storage, wind, and gave us a mix of assets instead of just a natural gas solution. But both 1C and 1D excluded the transmission option. So what we learned is that with the growth as it was, which, so this is the winter loading over time, and then this is our summer loading. So it's a significant difference in winter to summer. And as I said, the winter was only occurring a couple hours out of the year. And if you looked at what you can do from a distributed generation standpoint, I can meet the contingency thresholds locally to the load, and I can do it in a way that defers the cost over time. So I can, in the first year, say, if I need 50 megawatts, well, I can put in 50 megawatts at a cost, and then as that load grows, if it grows, which it may not, I can grow my solution to meet the need. With the transmission solution, it's a one-time cost up front that will cover the area for an extended period of time, but all the cost is in the first year. So what do we take away from this example is I think we need to not think of these in isolation. So wired versus non-wired alternative. It's, I have a wired solution, and what non-wires alternatives am I going to layer on top of that as an alternative? The technologies that are available, it's seemingly infinite. So from a planning perspective, if I say I'm going to use a battery, you know, there's a use case for a battery, and I think Neil gave a good presentation on, you know, the different uses of batteries. But you know, control systems for these, there's, in my mind, a difference between, all right, we've planned a feasible solution, and then designing the all the benefits you can reap from these new technologies are two separate evaluations. I think we need to first prove that something's technically feasible for the planning criteria, and then in that system, and then work to reap all the benefits from that solution. Similar to the presentation this morning from Dominion, we need to have zero friction. So how do we get from the data that's available to a solution with as little manual effort as possible? So in most utilities we talk to, the two biggest issues are in the model development and missing data, primarily in a SCADA system. So there's some cleanup that needs to be performed from the raw data to the Synergy model, and then ultimately to a analysis that's performed. We need to leverage Synergy. So there's traditional features that are in here that have been in there for a long time: load allocation, load flow, fault current analysis, coordination, and all the elements that go along with that. Not to say that these won't change as we need to adapt controls for different devices, but we need to take advantage of the newish features that are in the solution. Time series analysis, taking advantage of the solver to script and automate digest of the model and the output of the model. And we're going to be modeling new elements that we never modeled before. How do we handle electric vehicles, solar, wind? These are things that when you start considering that Synergy has the capability of, and Larry's invested in making sure the solution works for everyone. So we need to make sure that we're using these features and giving feedback to Larry and his team. I touched on load forecasting a bit, but historical trending only tells us about the past, not necessarily about the future. And we have instability in that and this is regionally dependent, but solar penetration, time of use rates, electric vehicles, all of these things are going to change and not trend with the growth trends of the past. So we need more mature load forecasting tools that allow us to feed the model appropriately. I've learned that programmers are awesome. So we have engineers that dabble in programming, but then we also have programmers and data scientists and solution architects, and all the work that we've done here. This is a group project that I happen to be presenting on. We have a larger team that they've worked really hard to make progress in this area. So, if I tried to do something, it would take me forever to get from, like you'd asked about the, how do you get started? So, I was there. I was like, oh man, this is overwhelming. But bringing in other people from different backgrounds really benefited that cause. So, we brought in a programmer, and what took me seemingly a month, he was done with in a couple hours, and not really understanding why it was taking me so long. But I see a future of a mix of not just engineers, programmers, data scientists, solutions architects. And then there's the data management. So in our example, we had a few feeders, but if you imagine 3,000 sections and trying to run that for a year and capture 4 data streams, we're at 100 million records. It's not something that you can work through in an easy way. You really need some data reduction. So taking it down to what's necessary data and what's noise. So something Larry's talked about is, instead of doing 8760, we just started a lower profile. So maybe that's a 288 or 576. And I think that is a good approach until we learn more about the value of time series analysis, and we do it more. And ultimately, when the processing gets to the point where we can run it in a timely manner, maybe we'll go to 8760 and we'll look at all the benefits that can come with having all the data. But at this point, we're still transitioning from how do I go from peak to a day profile, or how do I go from peak to a longer multi-scenario profile. When we were looking at the financial considerations, valuing non-wireless alternatives, each utility is going to have their priorities. If it's reliability, CO2 reduction, what I think we're going to see is some utilities will value not just the customer satisfaction of, and less truck rolls through reliability improvement, but we may also see valuing the local community impact. You can, there are estimators out there for what does it cost for an outage, and not in terms of the utilities cost, but in the local economy, what does it cost them? But ultimately, we get through all of this, and the process really hasn't changed. We still have study inputs, we still do analysis, we come up with projects, we validate the projects, and then we end up with a preferred plan. So from a capital planning perspective, the incorporation of time series analysis didn't change the way that we go through our workflow. It just increased the amount of analysis that's being done. So next steps, as I mentioned, this is kind of a group assignment for us. We've got some, at LEIDOS, we have R&D in place to see how we can expand in this space. So the way we see it is that there are tools in place that can do load forecasting. Synergy is a tool that you can use for engineering analysis, but there may be a gap on the back end that once we produce all the data, what do we do with it? So that's a space that we're exploring. We've made a lot of progress in how to visualize the output of all the time series analysis, more for internal use than external use. Not to say that we wouldn't share that with someone. But what we really see, that's a phase one. This is really feeding into our ultimate goal. What we want to do is develop logic that help with not only developing output, but helping with solution matching. So with a huge number of options that are available, how do we pick the ultimate option? So, in the olden days, before time series analysis, that isn't really a thing yet, we would look at the peak, and it was understood how you would get from, I have a voltage problem, what are the steps to go through to solve the problem? Well, that can be scripted, but there's an infinite number of options that are available when we start talking about non-wireless alternatives. And to do that manually, I think there's a step we can take in that direction to automate recommendations that the engineer will then review and validate, and then ultimately select the preferred options. So this is a vision we're working towards, and I think we're making great strides in. But with that, I'll take any questions. Are you doing 8760 or? Yeah. So I think there's some value in 8760, but without doing more and more of it, it's hard to. At volume, we're going to identify all the benefit streams, but in individual cases, it's kind of hard to identify all the value that you can get out of it. So, all right. Yes, I don't see a reason to call this non-wires alternatives. It should just be alternatives or solutions. So it's a buzzword in my mind that eventually will just go away and we'll just develop solutions. All right, appreciate it.